Okay, so next we'll look at a discrete space. So let the set X be a countable set. And let tau sub d be the power set of X. That is the discrete topology on X. Then, for every point in the space, the singleton containing that point is an open neighborhood of the point X, such that the intersection of this singleton set with the entire set is the singleton set. And so every point in the discrete space X is an isolated point. Of the space X. As we will see, the number of isolated points of a given topological space is a topological invariant. That is, any space that is topologically equivalent and very soon we will use the term homeomorphic. So any space that is topologically equivalent or homeomorphic to the given space must contain or must have the same number of isolated points. So notice that we are not saying that two homeomorphic spaces must contain the same isolated points. Rather, they must contain or have the same number of isolated points. Okay, new definition. Let X be any non-empty set a partition of the set X is any collection of non-empty subsets of X such that the space, the entire set is the union of those subsets, and those sets are pairwise disjoint. So again, a partition of a given set X is any collection of subsets for which the union of those elements is the entire set, and each of those elements are pairwise disjoint. They have no elements in common. So let's first prove a small lemma. let A, B, C, and D be sets such that A is a subset of B and C is a subset of D. Then the intersection of A and C is a subset of the intersection of B and D. So proof, let the point X be in the intersection of A and C. Then the point X is in the set A and the point X is simultaneously in the set C. Now as the point X is in the set A and A is a subset of B, that point is in the set B. And as the point X is in the set C and C is a subset of the set D, that point is in the set D. And so the point X is in the intersection of B and D, and hence the intersection of A and C is a subset of the intersection of B and D. So let X together with some topology tau be a topological space. And let the set A be a subset of the space X. We have already demonstrated that the intersection of the boundary of A with the interior of A is empty. So now we look at the intersection of the exterior of A with the boundary of A. This is the intersection of the exterior of A with the complement of the union of the interior of A with the exterior of A. So the two sets have no points in common, and so the intersection is empty. Now the interior of A intersected with the exterior of A is the intersection of the interior of A with the interior of the complement of A. Now as the interior of the set A is a subset of the set A and the interior of the complement of A is a subset of the complement of A, we have that the interior of A intersected with the interior of the complement of A is a subset of the intersection of set A with the complement of A, which is empty. That is, the intersection of the exterior of A with the interior of A is a subset of the empty set. Now, since the empty set is a subset of any set, in particular, it is a subset of the intersection of the exterior of A with the interior of A. We have set inclusion in both directions, and so the intersection of the exterior of A with the interior of A is empty. So if the boundary of A is not empty, the interior of A is not empty, and the exterior of A is not empty, then the set consisting of or containing the boundary of A, the interior of A, and the exterior of A is a partition. of the space X. Okay, new definition. Again, let the set X together with some topology tau be a topological space. A separation of the space X is a pair, which will denote U and V, of non-empty proper open subsets of the set X that form a partition of X. So notice once again that for a separation we need a pair of non-empty, proper, and open subsets of the set that forms a partition of the set X. A topological space X is connected if and only if there does not exist a separation of the space X. Otherwise, the space X is disconnected. So next we'll prove a theorem that gives an easy way to determine whether or not a given space is connected. A topological space X is connected if and only if the only subsets of the space X that are both open and closed are the empty set and the entire set. So proof. We will prove the contrapositive and this is the statement that a topological space X is disconnected if and only if there exists a non-empty proper subset U of X that is both open and closed. So suppose that the space X is disconnected. Then there exists a pair U and V of non-empty proper open subsets of the space X that partition the space X. That is, X is the union of the sets U and V, and the intersection of U and V is empty. And so the complement of the set U is the set V, which is open. So the set U is closed, and hence there exists a non-empty proper subset U of X that is both open and closed. Now the same is true of the set V, but we need merely show that there exists at least one. So conversely, suppose that there exists a non-empty proper subset U of X that is both open and closed. Then, as the set U is closed, its complement is open. Further, the complement of the set U is not empty, since U is a proper subset. And since X is the union of the set U with the complement of the set U, where U and the complement of U are both non-empty, proper, open subsets of the set X that are pairwise disjoint, or which are disjoint. The set which contains the set U and the complement of U is a separation of the space X, and hence the space X is disconnected. So as we will see, connectedness is also a topological invariant. For a given topological space. So let's look at the connectedness of the spaces that we have been studying. We have already demonstrated that there are no proper, no non-empty proper subsets that are both open and closed in either the particular point topology or the excluded point topology. So spaces with these topologies are connected.